look at lab 4 parallel RC, RL and RLC circuits. In this circuit we will look at parallel RC, parallel RL and parallel RLC circuits. If you look closely, we have two sets of circuits for each configuration. This is parallel RC circuit, but this is the circuit that we are going to implement to get the required readings. So why this circuit is different from the one we are considering? Because we have discussed earlier that oscilloscope is a voltage measurement device, and we won't be able to measure current directly through an oscilloscope. Since we are studying parallel configuration, in parallel configuration we know that the parallel branches have same voltage, but the current drop will be, the current through each branch will be different because of the different impedances. So to measure the current, we are going to use resistance called sense resistance. So each component has its own sense resistance, which we will use to calculate the current of each of the component. So what the sense resistor will do is, we'll get a voltage drop across each sense resistor, then we will divide that voltage by the value of the sense resistor to get the current. The idea is that the current flowing through this branch will not be affected in phase by this resistance. So the voltage and phase of this sense resistor divided by the resistance value will give us the current and phase through this branch, and this is the same for each of the components. So for the RC circuit, this resistance, sense resistance, will give us the current through this branch. This resistance will give us the current through this branch, and this sense resistance will sense the current of the source. We will use this concept to study RC, RL and combined RLC circuit. So first let's start implementing the RC circuit. So we have gathered all the components required for this setup. So we need a 10K resistance, as mentioned in our apparatus list here, that we will need a 10K resistance. We will need other resistances as sense resistance, 3 1 kilo ohm, 2 3 ohm and 3 10 ohm resistances, 1 10 nanofarad capacitance, 1 33 nanofarad capacitance, and 1 33 330 microhenry capacitance. For the parallel RC circuit, I have collected the required components: the 10K resistance, 10 nanofarad capacitance, and 3 1 kilo ohm resistances. These are the 3 1 kilo ohm resistances. In the table for this experiment, for the RC circuit, we will need to measure the value of the practical value of the 10K resistance and the practical value of the 10 nanofarad capacitance, which we are going to do now. We set the DMM to the resistance measurement mode, and then attach the DMM probes parallelly to get the value. So we see that the practical value is 9.78 kilo ohms. So we will record that in our table. Since we will be using this same resistance for all our all three configurations, RC, RL and RLC, we will record this value for each of the R measured section of our table. Now we'll measure the value of the capacitance. To measure the capacitance, we are again going to use an LC ammeter. We're going to turn this on. This is a 10 nanofarad capacitance, so we'll put the range at 20 nanofarad and place this capacitor here. This is a non-polar capacitor, so the polarity really doesn't matter. We can attach any other. So if we attach it, we get 9.49, 9.48 or 49, 9.49 nanofarad. So we'll record that in our table. 9.49 nanofarad. So now we are ready to construct our circuit. So if we go to the circuit diagram, we see that we have two parallel branches, one with the 10K resistance and with the 1K series sense resistor, a parallel branch with the 10 nanofarad capacitance with the series 1K sense resistor, and the source sense resistor of 1K here, and the source will be 3 volt peak and 1 kilohertz. So let's implement this. So I'm placing the 10K resistance here, and I'm attaching 1K resistance in series. Then, as per the circuit, the 10 nanofarad capacitor is connected to this node A, that is this end of the resistance. So I will attach the capacitance, one end of the capacitance with the resistor, and another one in a separate node, and then attach 1K in series. So we have connected this branch and this branch parallelly, because these both branches start at the same node and they end at the same node, fulfilling our requirement for the parallel configuration. So if you see closely, this branch and this branch start at the same node, node A, and end at the same node, that is it will be labeled node B. So now we will attach this 1K resistance in series to these two branches. I can do that by doing this. So now we have attached the 1K sense resistor for the source over here. One reason why we're placing this sense resistor for the source here instead of this location is because, as we know, we need one channel of an oscilloscope to measure one node voltage. So if this resistance was placed here, we would need two separate channels to measure the voltage. But by placing the sense resistor here, we eliminate that, because one end of this resistor is connected to the ground. So just node voltage VB is the source voltage, RS source voltage. So we eliminate the need for multiple channels by placing this resistance here. Okay, so our components have been connected. We now need to connect the source with this circuit. To connect the source, I take the voltage probe of the function generator and place the red end to this node A. And this black end to this end of the sense register. Okay, so we have connected our circuit as dictated in our circuit diagram. Now we will power up the source and set the source to the required 1 kilohertz and 3 volt peak configuration. As previous, we turn on the function generator and we see that by default now the frequency is 993 Hz and the source is triangular. I need to change this source to sinusoid because we're giving input as a sinusoid, so I change the source to sinusoid. I increase the frequency to 1 kilohertz and we need to set 3 volt peak, but we wouldn't be able to do that using this display. We need to set the peak voltage using oscilloscope. We will now need to attach the oscilloscope with our circuit. So this is the channel 1 of our oscilloscope, and I'll place this ground probe to the ground of our circuit, and this positive part of our circuit to node A, this node, the one node. Okay. Now our oscilloscope is connected with parallel to the source, so we can set the source voltage to 3 volt peak. So this is the source voltage being displayed by our oscilloscope. So as always, we should set the channel 1 coupling to AC, channel 2 coupling to AC, because we are setting the circuit for AC input and output, so both of our channels will be for AC. So now we can turn off channel 2 since we have not connected anything, and adjust this channel 1. So we have, in this condition where the graph is out of display, we will not be able to get proper measurements either through cursors or through measure. These values doesn't make sense if your if your signal is out of bound of the screen. So we need to adjust it accordingly. So I can reduce the channel voltage per division and increase the time division to get the display to a meaningful setup. We need to set channel 1 to 3 volt peak. We see that by default here we see channel 1 Vmax, so it's currently 4.48 volt. We can alter the amplitude by rotating the amplitude knob until we get 3 volt max. So we have bit of fluctuation, but okay, there's a bit of fluctuation, but we'll take it to be 3.04 volt, which is our required input, and frequency is 1 gigahertz, which is being displayed here, and also we have seen the value in our function generator screen. Now we will attach channel 2 to node B. So this will go to the ground. The black wire always goes to the ground, and the positive wire will put the positive part of the probe will connect it to node B. Node B is in this end of the RS source. So I'll attach it to the circuit, and so I'll attach it to this end of the RS source, which is the node B. So now my channel 2 is connected to node B. In this condition, when channel 2 is connected to node B, it will enable us to record the voltage of RS source, because channel B is giving us VB, and VB is the voltage of RS source. And since we have channel 1 connected to node A, that is the source voltage, we will be able to calculate the phase. Although channel 2 is connected, we cannot see any graphs on the screen. To get the graph, we need to turn on channel 2. Once we turn on channel 2, we see that the graph is being displayed. So channel 2 is connected to node B. Channel 2 is giving us the voltage waveform of RS source. So if we go to measure and place channel to Vmax in this box, it's entered your choice which box you choose. I'm choosing this one, and since we're going to take a reading of a voltage, the category is voltage, source should be changed to channel 2. So if I press return, channel 2 Vmax is 360 millivolt. So 360 millivolt is the peak voltage of RS source, and we should record that in our table. In the data table, I have calculated the theoretical values and recorded them here for ease of understanding the outcomes. So we have measured that for IS we are using RS source. The V sense measured is 360 millivolt. So that is the value for the peak voltage across RS source. So now we need to measure the phase. We can measure the phase using two methods. One is using cursor, as we have seen previously, and a second method is using the built-in measure function. So to use the built-in measure function, let me use this box. So I'll go here, I'll go to delay, channel 1 to channel 2, phase. The phase is not being shown. So it's around 323 degrees. Subtract 360 from that, it's around 38 degrees. We can use this method, and by using cursor, we need to press cursor, change the mode to manual, tap to time, sources channel A. We'll take this to a peak here, this one here. So I have placed one cursor at the peak of channel 1, the source, and another cursor at the peak of channel 2, the RS source voltage, and we see that the difference is 80 microsecond. And if you see with reference to the axis, the blue curve, the channel 2 curve the peak appears before this channel 1 peak, so this voltage is leading, so the RS source voltage is leading, so the symbol should be plus. So we measure the delay to be 80 microsecond and the symbol is plus because of leading. Using the calculator, we calculate that the angle is 28.8 degree plus 28.8 degree. By dividing this voltage with the resistance sense resistor, which is 1K, we find that the I peak practical is 0.36 milliampere. So and since using a resistor, the phase would be same for both the voltage and the current. So our required reading for the source is complete. Now we move on to the resistance. So if we go back to the manual to calculate the voltage across this sense resistor, we have to move the channel which is connected to node A to node C, so that we can use the concept VC minus VB would give us the voltage across the resistor. But we know that the channel connected at A is showing us the source voltage, and to measure the phase we need to refer to the source voltage. But if we move this channel from node A to node C, we will no longer be able to get the source in our screen. So before moving channel A to channel C, we have to save this source voltage in a reference using the ref function of our oscilloscope, and afterwards we'll move channel 1 from node A to node C. By using the reference function, we will save channel 1, which is the source voltage. So I don't need the cursor now, so I will turn off the cursor for now. So to save the channel 1 in reference, I press the ref button, then source is channel 1, which is true, we are using channel 1, and the time base should be 250 microsecond, otherwise we will not be able to use this manipulate this reference signal, because if time base change, we will no longer get a proper orientation of the waveforms. So I'll save it in reference A. So reference A is selected, I'll just press save. Okay. So channel 1 has been saved and it is being displayed in reference A. Now we will move our channel 1 to node C. So after saving the source voltage in our reference, we'll move this channel to node C, which is in between these two resistors. We see that after moving the channel, the signal is no longer triggered. To fix this, we can press set to 50%. Because it's not working, we press trigger menu and choose channel 2, and we see that our signal has been triggered. So now we can implement the math operation to get the voltage of the sense resistor RSR. To do that, we press math. Channel 1 is source A, channel 2 is source B. Operation should be minus. So this new purple signal, this is our RS, voltage across RSR, the sense resistor R. And to get the values of this signal, we have to use cursor. By using cursor, first we will measure the voltage. The type should be time, and the source should be math. We move cursor B to 0 volt and cursor A to the top of our math signal, 320 millivolt. So 320 millivolt is our peak voltage for the RSR. So we record So we record 320 millivolt for our RSR. So voltage across this resistance RSR is 320 millivolt. Channel 1 minus channel 2, node C minus node B is the voltage of the sense resistor R, RSR. So this two signal is the voltage of the sense resistor RSR, and this gray signal that is for distinction, we see that manipulating channel 2, we see that this is our saved reference voltage Vs. So by looking at the graphs, we see that the RSR voltage is slightly lagging. We will use the cursor to find the value. That's time. Let's use the source to be math. So we see that the delta t is 20 microsecond. So the phase difference is 20 microsecond, and the blue signal is lagging. It's slightly behind the source resistance, source voltage. So we will record this as 20 microsecond, and since it is lagging, the sign should be minus. We record 20 microsecond as time delay. It's lagging, so the symbol is minus. Using the calculator, to find that the angle is 7.2 degree. Moving channel 1 from C to D and repeating the same process, we can find the peak voltage of RSC and the phase of RSC. So when I move channel 1 to node D, the voltage of RSC would be voltage of D minus voltage of B. So that would be channel 1 minus channel 2. So let's do that. After shifting channel 1 to node D, we perform math. Channel 1 minus channel 2, which is D minus B. So this purple signal is our voltage across the sense resistor for the capacitor RSC. So in this configuration, using cursor, we can measure the voltage and phase of this signal. So if we measure the phase first, this one cursor should be at the peak of the source, which is the reference signal which we saved earlier, and one should be at the peak of the purple signal, which is our RSC voltage signal. So we find that the time difference is 230 microsecond, which should be recorded in the data table. Additionally, we see that the peak of the RLC voltage appears before the source voltage, so the voltage is leading, so the symbol should be plus. So we find that the angle is 82.8 degree. To measure the voltage, we have to change the type cursor measurement type to voltage. Cursor B is already at 0. We move cursor A to the peak. It's 200 millivolt. A bit less than 200, it's 160 millivolt. Which is 0.26 milliamp. For the parallel RL circuit, we have been considering this circuit where we have placed RS source here and R1 and L1 is here, and sense resistors for resistor and inductor are here. We are facing some problems in measuring the voltages across this resistance and this inductance. We have been facing some problems in measuring the voltages of these two sense resistors because of maybe some internal calculation errors due to the voltages being low. So we will restructure this circuit just a bit. We know that RS source will help us to measure the current of the source, and we have just placed this source for ease of measurement. But if we place this source here, this will be the same circuit and it will still help us get the required value. So we'll restructure this circuit as this. So this is still R1, this is still the old RSR, this is L1, this is RSL, but I have moved this RS source to the top, so this is now RS source. We'll need to relabel the node names, so I'll keep A for this, C for this, B for this, and D for this node. I'll rename this node E, A, B, C, D, E. So this is the new circuit that we'll implement. So we had already implemented this circuit. We had already implemented this circuit according to the old circuit diagram, this diagram. Now we will restructure this circuit to follow this diagram. So we can easily do this by just moving this RS source to this node and creating this node. And if we connect the source here, we'll be completing the circuit. Now we will connect the function generator as our source. So I'll connect the black wire and the red wire of the source. If you see our modified circuit diagram, the red wire will go to node E and the black wire will go to node B. So I attach the red wire to node E, our newly created node, and the black wire to node B, which is located over here. So now our circuit is complete. We will now have to attach the oscilloscope accordingly. So first of all, we will need to tune the voltage source, and to do that we will need to attach one channel to node E. I will attach channel 1 to node E. As always, the black wire goes to the ground, which is node B in this circuit, and this positive portion will be attached to node E. which is here. According to the data table, we'll need to calculate IS, the source resistance, the source current first. We'll need to measure the voltage of the sense resistor for source first. So we will attach channel 2. We'll attach channel 2 to node A. So black wire always goes to ground, and I connect the positive part of channel 2 to node A. So I'll be able to set the source voltage using channel 1. Then I can use channel 1 minus channel 2 to get the voltage across this resistance, which will help me to calculate the current supplied by the function generator. Now I turn on the function generator by pressing this button, and the oscilloscope by pressing this button on top. Our required voltage settings is 10 kilohertz, 3 volt peak. So at first I adjust the function generator to give us 10 kilohertz. So if I reach the max position, we will not be able to get to 10 kilohertz. So I reduce the frequency knob, change the range to 10k, and now I can adjust it to 10 kilohertz. Okay. So our source has been set to supply 10 kilohertz. The default waveform is triangular. We'll change it to sinusoid by pressing this. So now we are ready to make the adjustments. Moving on to our oscilloscope, settings are set by default. I'll press the default setup to get to the default setting. First of all, before making any calculations, I'll press channel 1 and change the coupling to AC. Press channel 2 and change the coupling to AC. Now I'll change the horizontal knob to see the cycles clearly, and then I can adjust the horizontal vertical controls to see the waveforms as I need. So from measure, I see that channel 1 voltage peak to peak, channel 1 Vmax is already displayed in this this section. So I'll need to set channel 1 Vmax to 3 volt. I can do that by adjusting the amplitude. I'll adjust the amplitude until channel 1 Vmax is 3. So channel 1 Vmax is 3 volt, and now our source has been set. Now we can take our corresponding readings. Since our channel 1 is connected to node E and channel 2 is connected to node A, node E minus node A would give us the voltage drop across the sense resistor for source. So we can do that by pressing the math button here. Channel 1, channel 2, operation is plus. We press this to take it to minus. So this is the waveform for the sense resistor for the source. We'll need to measure the peak voltage of this curve and also the phase of this curve. So first of all, to measure the peak voltage of this curve, we will need cursor. We turn it on by pressing manual. The type is voltage. Source should be math. And to measure the peak voltage, we take cursor B to 0 volt and we move cursor A to the peak of the curve. So we get 480 millivolts. We should record that in the table. So our measured value is 480 millivolts. Now we'll need to measure this delay delta t, from which we'll find the theta. Okay, we will change the type to time, since we are measuring time now for the delay. Notice with reference to the axis, channel 1 is our source voltage. The peak of the source voltage appears before the peak of our resistance voltage. So this means that this voltage waveform for the sense resistor of source is lagging. So the sign should be minus. And I now move cursor A to the peak of the source voltage, and cursor B to the peak of the waveform. The value is 17 microsecond and the symbol should be minus. Symbol should be minus, since this voltage is lagging. Now we calculate, sorry, this should be recorded here, 17 microsecond. By calculation, the phase is 17 microsecond into 10 kilohertz into 360 degree. It's 61.2 degree, minus 61.2 degree. Now we move on to the sense resistor for the resistance, which is this one. So for this we have to move, so according to this we have to move our one of our channel to this this resistance C, to this location, node C. So if we attach one of our probe to node C and another is connected to node E, we will be easily able to determine the voltage of this sense resistor and the phase accordingly. So since we have completed calculating RS source, we can move channel 2 from A to C, which I am doing by moving this from A to C. So I have moved this channel from this node A to this node E. Now we can turn off the math function, and channel 1 is our source and channel 2 is our voltage drop across the sense resistor for the resistance, and we can easily get the value of the sense resistance from our measuring tool. To get accurate readings, we should utilize most of the screen. So I have decreased the volts per division for channel 2. Now if I press measure, I don't see channel 2 Vmax here, so I should bring the reading here. So I can just press this, go to voltage, change to channel 2 and go to Vmax. So we find that the value is 236 millivolt. We should record that in our table. $236 millivolts. So now we'll measure the phase. On the oscilloscope screen, we see that the channel 2 curve is leading. It is leading because the peak of channel 2 appears before the peak of channel 1. So we'll measure this delay using cursor. The source should now be changed to channel 2, and let's move one of the cursors to peak of channel 2, another to the peak of channel 1. Okay. 5 microsecond is the delay, and the symbol should be plus because it's leading. 5 microseconds, symbol is plus. We measure the theta, 5 microsecond, f 10 kilohertz, 360, 18 degrees plus 18 degrees. So that is our phase for this sense resistor. Now to take the reading for this sense resistor for inductor, we have to move one of the channels to node D. We have connected channel 2 to node C, we will move it to node D. So I am removing this channel 2 from node C and attaching it to node D. So now channel 2 should give us the voltage across the sense resistor L, RSL. We see that channel 2 waveform is out of scope, so we reduce channel 2. Now if we go to measure, we find that the voltage is 424 millivolts, channel 2 Vmax. We should record that in our table. We press on the wires so that we get a good reading. We see that the new reading for channel 2 Vmax is 400 millivolt. We should readjust our reading, 400 millivolt. For the phase, with reference to the axis, we see that the channel 2 curve is, the peak is appearing after the peak of channel 1, which is the source. That means this channel 2 is lagging, so the symbol should be minus, and the value of the time delay is, we manipulate the cursor, take cursor A to the peak of channel 2. Cursor B is already at the peak of channel 1, so 17 microseconds. So 17 microsecond is the time delay. We will record that in our table. The symbol is minus because of lagging, and you see that for 17 microsecond we have 61.2 degree as calculated before. So we have calculated all the necessary readings for our parallel RL circuit. For our third experiment, parallel RLC circuit, we will use the same modification that we used for the parallel RL circuit. That is, we will shift this source to this location and take our readings accordingly. So reconfiguring the circuit, we have the source here, and we replace the RS source here. So we have R1, RSR, L1, RSL, C1, RSC, and this is RS source. So we have just shifted this to this. So we have reconfigured the circuit. The node names will be as previous. We will not rename any. A, C, T, E, we'll call this node B, and this one F. So we'll be constructing this circuit. So if we look at the circuit, the source resistance for the sense resistance for the source is 10 ohm now. The sense resistor for inductor is 10 ohms, and that of the capacitor is 10 ohms, and the capacitor is 33 nanofarad. Before constructing the circuit, we should record the practical value of this capacitor of 33 nanofarad. We'll do that by using an LCR meter. Turn it on, take it to 200 nanofarad region. I take my 33 nanofarad capacitor, attach the crocodile clips, and take the reading from the display, 33.5 nanofarad, which will be recorded here in our table. 33.6 nanofarad. So now we are connecting the circuit as per our modified diagram. So we have just replaced this sense resistor with the 10 ohm one. This branch remains same, and the sense resistor with the inductor has been replaced with 10 ohm. And now we are going to attach a capacitor parallel. So I have already attached the sense resistor. Now attach the capacitor. So our circuit is complete. As you can see from the circuit, if you observe from the circuit, RS source has been placed here. We have a parallel branch with R1 and RSR, R1 and RSR. With that, we have in parallel inductor L1 and sense resistor RSL, inductor and sense resistor RSL. Then parallelly we have capacitor and RSC. We have placed capacitor and RSC. We have placed a wire to complete this connection. Now we will attach the signal generator. The red wire, the plus polarity of the signal generator, will go to F, and the black wire, the negative polarity, will go to B. So the red wire is attached to F, and the black wire is attached to B. For measurement, we will connect channel 1 to F so that we can set the source amplitude. And for the first reading, for the voltage across RS source, we will place channel 2 at node A. So placing channel 1, the black wire always goes to the ground, and this plus end, attach and wire, will go to node F. The second the second channel, channel 2, I'll attach the black wire to node B, or the ground, and the positive end will be attached to this node A. So channel 1 is at F, channel 2 is at A. So channel 1 minus channel 2 will give us the voltage across this resistor. So I turn on our function generator, and we see that the output is 6 kilohertz. We need 60 kilohertz. So we press the 10K button. Now we see that we have 60 kilohertz. If we need to adjust, we can use the frequency knob. the default output is triangular, we'll change it to sinusoid by pressing this button. Now we turn on our oscilloscope by pressing the button on top. The oscilloscope is turning on. We'll need to adjust according to our requirements. So channel 2 is gone out of scope, so we bring it into focus by turning the vertical knob for channel 2. In channel 1 Vmax, we see that the voltage is 4.72 volt peak, but according to our circuit diagram, we need 60 kilohertz 3 volt peak, so we'll set the amplitude to 3 volt peak. So we adjust the amplitude to 3 volt peak. Now channel 1 minus channel 2 would give us the required voltage, the voltage of the RS source. So we can do that by pressing math. Channel 1 is source A, channel 2 is source B, and operation should be minus. We just run a little check that if our coupling is AC. So channel 1 is AC, channel 2 is AC. Okay, so we are ready. We reset the math so that, okay, so this math signal is showing the voltage across the sense resistor RS source. To get the value, we need cursor. Turn the mode to manual, type is voltage, source should be math. Cursor B should be rotated and taken to 0 volt. Observe the value that and stop at 0 volt. Okay, now if cursor B at 0 volt, cursor A should be taken to the peak of this curve. At the peak, we have 200 millivolt. This should be recorded in the table. So we have 200 millivolt. We have recorded 200 millivolt for this. $200 for this. Now I need to measure the delay. To do that, we'll change the type to time. So the curve is flat, so we can adjust it so that we can make the curve larger and get a better value. To do that, we go to the math operation menu, go to the next page and choose this option and rotate to increase. Now if we go to cursor, the type is time. Let's bring cursor A to the peak of the purple signal and cursor B to the peak of the yellow signal, our source. So we see that the time delay is 2 microseconds and the purple signal is leading because its peak appears before the peak of the source, that is channel 1. So the symbol should be plus. Delay is 2 microseconds and the symbol is plus because the signal is leading. So for 2 microseconds we calculate that the theta is 43.2 degree. The symbol is plus. Okay, now I have calculated the time delay and the peak voltage for IS source. Now looking at our circuit diagram, we can move channel 2 from A to C, and since node B is connected to ground, we can just look at peak voltage of channel 2 to find the voltage of RSR. So I'll move channel 2 from A to node C. On the oscilloscope, I'll turn off the math function. I'll no longer need it. Channel 2 is small, so I change the volt per division to cover maximum area. I go to measure. I see that the channel 2 Vmax reading is being shown here, 228 millivolt. This is the reading for the RSR peak voltage. So we'll record that here. 228 millivolt. Now we need to measure the time delay. We can do that by bringing the cursor. The source should be channel 2. Take one cursor to the peak. So two of the cursor should be located at the peak of the two waveforms. So 400 nanosecond is the time delay, and by reference with the axis we see that the peak of channel 2 appears after peak of channel 1. That means channel 2 is lagging, so the symbol should be minus. Symbol should be minus, and 400 nanosecond. From calculator we can measure to be 400 nanosecond, 60 kilohertz, 8.64 degree. Now we can move channel 2 from C to D to measure the RSL peak voltage. So I'm moving channel 2 from C to D. Now from measure we see that the channel 2 Vmax is 324 millivolt. We can record that in the table. The value is 312 millivolt. We can measure the time delay by using cursor. Cursor A. Let's move cursor B to the peak of channel 2. Cursor A is already at the peak of channel A, so 3.7 microseconds. And by reference with the axis we see that channel 2 is lagging, so the sign should be minus. So 3.7 microsecond lagging, so minus. So the value is 3.7 microsecond, 60 kilohertz, 60 degree, 79.92 degree. Finally, we will have to move channel 2 from node D to node E to measure the value of RSC. And move channel 2 from node C to node D. From channel 2 we see that the peak voltage is 312 millivolt. We record that in the table. The time delay can be found by using the cursor. (3.7 microsecond), and with reference to the axis, the channel 2 waveform is leading, so the sign should be plus. And for 3.7 microsecond we have calculated earlier that the angle is 79.92 degree. So we have completed the parallel RLC circuit and taken all the required measurements from our devices.